actually is a decision? Let's start with that. So, so I work for Britannica, and Britannica is kind of a de facto standard in terms of anything that gets published there is, authentic and very well received by the entire, community in terms of, this is the final authority. So what Britannica has to say about decisions. So some of the keywords, if I look at, so it talks about analysis. There is an element of prediction. There is an element of information. Then references are taken. Models get created, devised, at least while you are taking decision. There has to be a context to the decision, and then every decision has an element of uncertainty. Now let's talk about decision-making process. What actually is a process? If I have to make a decision or you have to make a decision, you will probably look at the data. You will understand that data, and then figure out what will happen in the future. If I do this, what happens? And then determine what to do. So now you had a data, you looked at probably 2 or 3 options, what can potentially happen, and then you will make a decision which one to actually look for, opt. And then once you opted that, finally you would like to do a causal inference and see whether the decision that you have taken has helped the cause or it didn't, right? Now quickly on machine learning. What actually is machine learning? So, and then there is a statistics bit as well. In current context, the difference or the line between statistics and machine learning is blurring. And holistically, if we look at machine learning, I would say it encompasses everything to do with models, data, algorithm, and then you have this element of prediction. You devices patterns, and there is a high element of computation or computing that actually is required to do machine learning. We all know, that machine learning is divided into 3 broad categories, supervised, unsupervised, and reinforcement learning. And we are going to talk about that in the context of the framework that we have set. And the framework is, again, data, understand data, then the element of doing some prediction. Once you have done the prediction, which prediction to take, at least, select one, and then doing a causal inference that the decision which you have taken had made sense, had contributed, or there was a problem with the decision and corrective action needs to be taken. So that's the framework around which we are going to talk about. So let's start with data first. What is data? And this is the data ecosystem that currently is there, and I would divide it into 2 broad buckets. One is the internal data, and the other one is the external data. So internal data are the data which is available to the organization, whether it is university, whether it is a large organization or a small organization, they would have that data. Then that internal data, I would also include the data that the transactional data that you are acquiring from the product or the platform that you are offering. And of course, there would be customers' data in that. And then there are, so these are the data that you already have in the system, but that beyond that, we also have data which is available, externally, which is available on the social media platform, government data, and then there are, other third-party sources who are providing those data. So that's the data, I mean, the different variety and the sources of data that we have currently. One more data is the sensor data, that is the IoT data. And this is one data which is, coming at a really fast rate. Now, let's look at an internal data and what actually is and what's the big challenge that organizations are facing. So the way the organization has grown, I would say, diverse set of products or tools they have employed for different functions. And an organization is divided into multiple functions. You have HR function, manufacturing function, finance function, then, corporate management, then, supply chain management. And all of these organizations or rather functions have, at some point deployed a very pinpointed product or a tool to solve their specific problem. And what has happened is that has created a silo between the functions and the data as well. So data are residing in these silos in a specific format, which is not available to the data science at a holistic level. So that is the big challenge that you start with. And as I said that, for decision making, data is the starting point. Now let's talk about the external data. And as I said that we will be talking about some of the use cases. So this is a use case of a product or an entire organization which actually started on an external data. And they didn't have any internal data to start with, but they leveraged the data which is available in the public in the public domain, which is, say, the OTAs or the websites, and used that to create value for the customer. So, for example, let me tell you what is happening here is that you have this hotel data or airlines data, which is the pricing data, which is available on the social media platform, as well as it is available on the OTA site. So, Make My Trip, yatra.com, booking.com, so all of these websites, they publish hotel and airlines data, which is available to general public, and it's a public data. So there are organizations who are tapping into the data which is already published. So there's like 365 days of price data for all the hotels, and providing competitive intelligence to the hotel that, based on your competitor set, what the report looks like for the 365 days, what the other hotels are actually pricing, their specific rooms. And based on that, their revenue managers or their pricing engine sets their own internal data. Internal prices. So this is a classic example where, an entire external data source could be used to create value for an organization. And once you have this data, you can actually use that to do some prediction on top of it. So that is the rate forecasting. So that is your pricing forecasting for the entire 365 days based on your competitive intelligence, as well as some third-party data sources would be like, what's is there any events happening there? What is the weather pattern? And, and the correlations between weather and, some other factors that you can actually include. So this is, a classic use case of external data being used to create value for the customer. And the same would be with the reviews data. So for example, Amazon can actually give you a good indication on a specific product just by looking at those reviews, making some machine NLP based say categorization or topic modeling, where they can translate that into a specific KRAs or KPIs for the product creator, so that they can understand and relate what are the issues that the customers are facing just by looking at the reviews. So because again, like these are text data, very difficult to analyze, but there could be tools which can put that or categorize that into specific buckets, and one of the tool is topic modeling, and it is very widely used for review analysis. Now, as we talked about internal data source as well as external data source, one of the things that data scientist or the data engineer has to do is to bring or create a holistic picture of the entire data sets that an organization can leverage. And for that, you need to create a data lake, which would, I would say, acquire data from both on-premise or or not only on-premise, but as well as all the products which is in-house. So you get all those data into the single data lake, as well as real-time data that is coming, which is the transactional data, and then third-party data. So all the data actually, in its raw form gets into the data lake. And on top of data lake, you do analysis as well as machine learning. Techniques to get your data into the data lake. So if you already have products which has its own databases, ETL is one of the techniques to actually get those data into the data lake. And then, of course, I have not represented here the real-time transactional data, how actually you get that into the data lake, but we are going to talk about that very soon. And then once you have this data in the data lake, then specific to your business needs, you create data marts, and on that data mart, analysis and BI tools are created. So that's generally how the large organizations are doing it, getting their data into one unified data lake, and after that having a data mart, and on that data mart you create specific views for your line of businesses, and then business intelligence tools and other queries are written on top of that. And in the real life modeling case as well, when you go and create machine learning models, these data marts become relevant, and I'm going to talk about that in a couple of slides from here. As I talked about, that real-time data is very, very important if you have a product where a transaction is happening. And not only that, but as we see how people want to do it, and it has to be kind of a real time. So for example, if you have a website where you have to do a recommendation, currently what is happening is that it is based on previous historical data, and we are doing those recommendations. But how about looking at customers behavior in terms of what actually they are clicking on which page, their behavior? We actually on real time actually make a decision and have a recommendation or a suggestion to that specific customer, or something that we kind of look at. And I think some of the very advanced products like Netflix have real-time recommendation engine. So if you click on a specific thing, or from where actually which tab you are coming to the movie view, your recommendation is going to change on the real-time basis. So what is happening is that we need a system which can capture real-time transaction or real-time event, and get that first of all stored in the data lake for futuristic processing, but at the same time be able to use that for analytics. And many organizations are doing that on the real-time data they are creating analytics layer, and combination of historical analytics as well as real-time analytics, which is being shown as a dashboard, and it is talked about as a near real-time and analytics dashboard. But what about using that data which is coming at the real-time in a stream fashion for your real-time recommendation within the model, right? So that's also the next wave of machine learning modeling that's being discussed, that is being researched and actively in use now, at least with few very advanced organizations. Understanding data. Let's we are still on the data. So now that we have the data in the data lake, we have to understand the data. And as a human being, I can actually look at one-dimensional data as a visualization, or at the most two. Three-dimensional, but still I'm not able to make much sense of three-dimensional. But beyond three-dimension, it is humanly not possible. So of course, if we have to present our data to to the management, we have to have some visualization. One-dimensional, two-dimension is really a good way of presenting it. The second is that, okay, if I have millions of features in the data, how do I actually reduce that to a simple one dimension, two dimension, or a three dimension number. So principal component analysis is one of the technique of doing it, right? And then there are k-means as a cluster. If you are looking at, you don't know about data and you want to see that and let the computer tell you a little bit of categorization or consolidating that data into certain buckets. Clustering is an algorithm, and both of these are like fall into unsupervised learning categories. And then, as I said, if you have to do visualization of text data, then again you have this topic modeling. We talked about it as a use case, and LDA is one of the models to actually look forward to. And there are many techniques, but I see Python as one of the language which has a very rich set of libraries available to achieve machine learning, and some of them are depicted here. So NumPy, Pandas, MATLAB, Matplotlib. Some of the libraries more around analyzing data and then doing some visualization. Scikit-learn is a tool which is predominantly used for machine learning algorithms. So it has a very rich set of algorithms which are there. These days, clouds also come up with pre-built algorithm. XGBoost is available on most of the cloud platforms which could be used. But still, as a data scientist, people are using scikit-learn and it's different versions of scikit-learns. So one is the base version. Then it has a version available for Spark. It also has a version available for AWS SageMaker. I'm not sure on Google, but these versions are they do have a version for Keras as well. So using those specific libraries would allow you to actually run it on production level distributed infrastructure. We talked about it. So that was about data. So that is how you understand data. There are Python tools that you can use, and there are other tools also which can be used for visualization. But the idea is that when you have a rich set of features, how do you actually get to a meaningful, a small number of feature set that could be analyzed, produced in a visual manner for people to make sense out of it, making some decisions out of it. As I said, the second step on the decision process is about making prediction. There are techniques of doing that. So regression, we will talk about classification, and neural networks can be used for making predictions, and that's the next step. I think we all know about regression. I'm not going to talk much about it. It's at high level, regression is about looking at the data set, and from a data set identifying the function which best represent that data set. That's what regression is. More important to understand is that while we are doing machine learning based regression, what is that important factor that we are looking at? And that is that error, which is the R-square error in case of regression. And idea is that what is the best error that we can achieve from the various different model that we can run on regression, and then based on that making a decision which particular model to use. That is what I wanted to highlight about. Again, talking about the tool set. If you are a Python developer, scikit-learn again has a very rich set of regression algorithm out there which you can try and use. Now, the second one that we talked about is classification, and what actually it is. It's about, again, as I said, both regression and classification are supervised learning. So in case of supervised learning, you know the outcome and you also know the input. And the idea is that you train that model or you train that algorithm to that specific set of output and input parameters. So what you have is that that output is defined, and from there you have this data set which you divide it into, say, training and test data set, and you use that training data to train that model. And once that model is trained, you test that against the test data, and then there it is not just one test that you run. You actually create create a few sets of test data and few sets of training data, and you run a combination of that on the model, and then you make a decision which actually, model is has given you a good set of result. So some of the classification algorithm which is out there is naive bias classifier. You have decision tree, support vector, random forest is there. Random forest can be used for linear regression as well, k nearest neighbor. So these are some of them. And the idea, if you look at, if you are a data scientist, what you do is that you kind of run multiple classifier algorithm, and then look at the confusion table, and then based on that make a decision which one is giving the best output which could be used in production environment. Bias and variance, let's skip that for now. Now let's look at as a data scientist, what is the workflow that you follow generally. So of course you have this data. That data is integrated, put it into the data lake, and after that there is this element of feature engineering that needs to be done, and it's one of the most complex things to do, where one of them is definitely reducing that number of features and getting to a set of features that can be visualized. Then target transformations. So many a times your target may not be in a format which could be fed into the model, so that transformation is there. And then feature extraction. So in coding we talked about that multiple features can that be encoded together to reduce certain features, and then looking at the correlations of feature versus the output, you kind of look at which are those features that could be used in your model. So that is like and as a data engineering, as a data scientist, if we are using working with data, this is where majority of the time of data scientists go in ensuring that data is in the format that could be used in the model. Then as I was saying, that you kind of go with multiple models, and then there is you run a cross validation to get to the best fitted model which can be used into the production. So this is again in terms of process. So with that, let me bring you bring the concept of auto ML. So what is happening is you have seen that data science is not an easy or a simple process. It's a process of experiments, where we experiment with data, where we also experiment with model, and any experiment is very difficult to quantify in terms of timelines. So wouldn't it be wonderful if we pass this big challenge of doing multiple feature analysis or feature engineering job to a computer to do that, and then similarly multiple model generation and model testing, if we can actually offload that task to a computer, and we as a data scientist look at the error as well as other parameters to make a decision which is the best model and what are the best data sets to actually use. And that is already available in AutoML. So some of the AutoML tools available there in the market are H2O.ai. Keras also has Keras Auto. These days, Google of course came up with AutoML. Azure also has an AutoML. SageMaker has a very interesting, and it has got launched this year itself. They have something called Autopilot. Most of the other tools that is there, you can actually, they will do all the model generation, they do data prediction, but you are not able to debug it. SageMaker actually lets you debug it. It gives you the entire code. You can make those adjustments in the code. Not only that, one of the challenge with data science is that the model which is generated or which is developed with a set of data, once actually it is deployed in the production, over the period it becomes stale because your data is changing, your environment is changing, right? And so even if the things which were good today, the model which you created today, in the future there is a good, rather it will change and your model will become obsolete. And that is where you know some that is where monitoring of the production model against your predefined errors is very, very important. And SageMaker is kind of doing that for you in a production environment. Data engineer and data scientists have to do it by themselves, but SageMaker has that. Now, SageMaker also has come up with a studio approach, and I don't know how many. I think people would know Eclipse. You would be familiar with Visual Studio. Some of the ID, which is very, very strong for writing code, doing debugging your code, connecting it with your QA environment, running it with simulations, as well as looking at tying it up with your CI/CD pipeline. All of it is available on Visual Studio, as well as good IDs like Eclipse. The same is now available through AutoML Studio approach through SageMaker. They have it all integrated together as a studio. So from one environment, multiple people can collaborate on it, create models, debug those models, run the testing, tuning of it, and then put it on production. And when it is in production, you are continuously monitoring it against the model, error rates and other parameters, to ensuring that the model is not stale. So pretty good advancement that has happened in this field. Very excited about it. Now that we have covered most of the things that could be done through model which is more mathematical, there are certain things which now with neural network or deep learning, machine can learn by itself. I think most of the people are aware of. So scientists have tried to mimic how human brains work through creating certain nodes and their core and their relationship between that. So one of the basic ingredient of neural network is that you have an input layer from where the inputs are provided. Then there is a second layer which is called as a hidden layer. On that you have the activation function, and then there is an output. Again, there is a function about it which actually narrows down from most of the hidden layers to actually achieve this output. This is this is part of, say, supervised learning, where the output is known to you. So for example, you have multiple images, you label those images against, like, this is a cat, this is a dog, and you have millions of them, and you actually choose one of the network and train that. And through back propagation, computer is able to identify the weights on each of the interactions. And then of course there are a little bit of complex things that needs to be done around bias, and if there are complex networks, we are going to talk about that briefly at high level. Some integration between the two different multiple components that needs to be figured out. But at a high level, computer is able to make sense of those and create a model. When provided the actual data, it will be able to classify and figure out that this is a image of a dog and this is the image of a cat, based on how it has been trained. Behind the scene, this is some of the models that's out there, and some of them are here depicted here. So multi-layer perceptron, we talked about it. Then there is a recurrent neural network, so where an input of one layer goes as an output to another. And then you have the LSTM, where there is a way of storing previous data. So these are the networks that we have from where we have the options to select one, and then train that model based on need. Now, what I want to emphasize on this slide is that these models are not just independent models, but these models could be linked together. And as I said that there are certain models which takes input as a so I probably don't have that depicted here, but there are models which takes input in a specific nodes, and that could be coming from a different model altogether. So we can have a very, very complex network of multiple models actually coming together to achieve the desired output. And again, here there are some level of experiments that needs to be done to achieve our objective. And the model that a related model that you are seeing here, or an integrated one, is about image captioning, where you have a CNN model, and then after that there are LSTM models which does the image captioning. So while we are here now, the question that is coming in mind is that, okay, now that we have all these models, how do we deploy these models in a production environment? So coming back, as a data scientist, what we get is a subset of data. We don't get the entire set of data to work with. Otherwise, it will be very difficult to actually, run those modeling exercise, doing those experiments. So we do it at a very small subset of data. So now that we have done that, and from there we have come up with some models which we believe are the best models, we need to test or run it on production environment. That is all the data that we have, and that is where the training of model has to be done. And it is a scale problem. It is not just a problem of data science or machine learning. Now it is a scalability problem. One of the tools that can be used, of course, Google will also have something similar. Amazon SageMaker is a tool on which models could be deployed. And again, as I said, if you are using scikit-learn or other, we have to ensure that we are using relevant libraries which supports distributed programming, and then those models could be deployed here and run against the entire data set and being trained and created a model. And that model gets deployed in in S3 as a repository, and from there we can also host that model on SageMaker itself, or we can run that model. And as I was saying that if you have a data mart, then many a times we run this model periodically to update that data mart with the output of our models. So let me give you an example. That let's say if I have some personalization data about my customer base, and every week I want to run those models against the new users that are coming onto my system, to update their personalization information in terms of whether they are say CRM customers, or they are ERP customers, or they are a retail customer. So those classification model, if I already have created, I would run that on a weekly basis and update my data mart every week. There could be certain use cases where models have to be deployed in a real time as an API. So SageMaker provides those endpoint interfaces as well. You deploy it there, and it makes it will be available as an endpoint for the applications to consume. Again, little costly, but again, it's based on use cases. But let's say if you're not a corporate and you want to save some money, you can still use open source tools like a Spark. Spark is distributed, and you will not have to pay for the services like SageMaker, which is managed services. So that tool pricing you can save, but yet we will have to pay for the cluster. But Spark is one of the way we can use it. The model could be created, the model could be exported, and that model could be deployed anywhere. You can deploy it even on SageMaker as well. So many organizations, even large organizations, what they do is that let's say they still have Amazon as their data big, they say data lake. S3 is big data lake. On top of that, you have EMR, which is Hadoop. Hadoop has a Spark on it. They build all these models on a Spark. They run it, create those models, and then deploy that model through SageMaker. SageMaker endpoint, or they will run it periodically and get the data updated in the data mart. So that is the way people are optimizing the cost of deployment. Now coming on to decision making. As I said, once we have this prediction, we now have model gets deployed, it is live in the production in the system, and it is being used. Now the question is that still we have to make some decisions, and prediction is one of them, and we have seen that. But at a high level, what is that framework around which decisions are made? So if I look at that framework, so there are two things. There is an environment in which a decision is being made, and then there is a data based on which the decision are based on which we take decision. And as we take decision, there is some change that happens in the state of the environment, right? That's what the entire framework is. So one is like if there are states where there could be the state dynamics could be high, state dynamics could be low. That means any decision is being made, the change in the state of the environment is either very, very high, very frequent, or the state is very low. Then there is an information rate where you are getting those information, or you have previous data and the frequency of data that you receive from the environment, which could be high, which could be low as well, right? So this is the basic framework of decision making. And I'm not going to go into the details, but from here onwards, what we are discussing is where majority of the complex artificial intelligence are built around. And if you look at most of the games, and even now, high-end, say, prediction or recommendation, and those things are also now going to be built on this framework. So quickly at high level, let me touch on this. So how and you to actually select certain techniques which are available and already in use, right? So how do you select that? So if your state change is fixed, and you say that the state is going to change infrequently, and you think that the information rate is low as well, and that is one of the case. Let's say you are doing a multivariant testing on the user interface, or you are doing an A/B testing where you have 6 or 7 interfaces, where your data is very, very low, and because you are exposing it to a very predefined set of users, and at the same time the change is also fixed. It is not that there is a very much change that is going to happen in terms of the activity that is happening, or the environment is going to change. So multi-arm bandit is one of the way of actually approaching, is a technique to actually use for that. Then you have a state change. Second one is like, let's say if a state change is very, very high, data rate is also high. So this is a case where, let's say you have this chess game, right, where Viswanathan Anand, you know all the moves of Viswanathan Anand, what actually he has played previously. So we have all of this data. As we change or make a move, the state of the board, which is the chessboard, actually changes. So how do you create a recommendation system, which moves actually to make? And for that, Markov decision process is one of them, is the tool. Similarly, if you remember AlphaZero Go, so that's the deep mind which was able to defeat the grandmaster of Go. So there also, Markov decision process was the key technique that they have used. Of course, they have done a lot of classification and those things to come up with the policies. But yeah, that was the technique that they have used. The other one is where the state change is very, very high, but the data is low. You don't have that much of data, right? And that is where, more, if you talk about, say, previous data I don't have, and I want to have this car, right, which is auto-driving car, or robots which are making decisions on the real-time data, that okay, this is this data I have, or I am simulating some things to actually come up with my own database, or data that I can use for recommendation, that what move to make, and what is the next move. And that is where reinforcement learning is the technique which is being used. Now, while we are talking about these, what the way that we have been talking about, about how machine learning has been used for supervised and unsupervised learning is a little different in case of reinforcement learning. In reinforcement learning, you have an agent which make an action on the environment, and when an action is being made on the environment, the state of the environment actually changes, right? And so this is the entire flow. So the agent makes an action on the environment, the state of the environment changes, and as the state of the environment changes, how actually it works is that it helps you in selecting the techniques to use in the decision making. So if there is a state change, let's say if it is fixed, and one of the example I was giving is you are doing an A/B testing, and you have, say, 2 or 3 screens which we are giving it to a specific set of users, and that is the data that we are getting back, and the data is also low, and the state also is not changing that much. You have just 2 or 3 different screens which you are testing. In that case, multi-arm bandit is a technique to use. The second one is where state change is very, very high. Your information rate is also very high. And the example would be a chess game where, say, Gary Kasparov, you have the entire previous history of how he has been playing, or as well as for Viswanathan Anand. And that could be fed, that is the data that you already have. And in terms of a state, as you make a move, the entire the board actually changes. So the state is also high, because then you have to do the entire calculations again. The technique to use there is Markov decision process. It's a technique which has been used by DeepMind for creating the AlphaGo Zero, if you remember, which defeated the Go Grandmaster. So this is what was used. Of course, before that, they had some classification and other, techniques that they used to create the policies that needs to be fed into the decision on the Markov decision process model. The third one is where your state change is definitely high. So, for example, we have a car, and it is making decisions on a real time. Inflow of data, or rather, the previous data is little low. What you are doing is we are making decisions on the real time, nature of the data, and that is where reinforcement learning. And similarly, so a few of those you can see on many of the games where reinforcement learning is being used. And there are a lot of set techniques, on reinforcement learning that's there. The Q model and others are there. But at a high level, reinforcement learning is unlike the other machine learning techniques, which is supervised and unsupervised. Here you have an agent. Agent takes a decision or takes an action, and that action directly fed into the environment. Environment's state changes. That state change gets back onto the agent as a feedback loop. And that's the entire flow. And how do you train the model in this case? So what happens is that you have an agent and you have an environment, and the agent is taking actions on the environment and taking some decision, and the state is changing, which is feedback. And then you provide certain kind of reward on that to that agent, which could be a point system, a 10 point, 20 point, 30 point that actually you provide to the agent. And the agent is supposed to achieve the maximum reward. And that is how it is being trained. And and this is an alternative process, and the process actually continues till this the agent come up with the most optimal actions that the agent can take to achieve the final reward. And here, the reward is not an immediate one. It is a futuristic reward, but how you set the policy is the most important and tricky here, so that an eventual success is being depicted in the policy, while immediate rewards on each and every action is being taken. So for example, losing a queen in a chess match to winning a game. So which one you would actually rate high? And these are the things where the policy design becomes very, very critical. At the same time, designing the environment is a little tricky. So DeepMind from Google is one of the tool set to look for. The other one is Neon Musk. He has created OpenAI Gym. Bill Gates has funded him. So that's another tool which is open source available. But these things, if you look at, so I think OpenAI Gym, I have looked at it. It is more game oriented, but we can use reinforcement learning in our real life problems also. So let me give you one example, and then we will close. The example is, let's say we are doing a recommendation for certain products on the website, and my agent could be any deep learning model which supports input parameter in a specific nodes, and those are the state change which directly feeds into that model. My environment is definitely the websites, and customers clicking on it actually making those state changes, which will feed back into the agent. Agent is a deep learning model which is taking certain actions. Action is nothing but recommendation. And then there is a reward mechanism. If you make a prediction and user actually accepts it, is the reward you give 100%, 100 reward back to the agent, and that is how the agent learns. And this actually, is the future where we see, reinforcement learning being now used going forward in advanced, tools to, do lot of real life use case problem solving. So with that, I'm going to close my session. That was the last session. If there are any questions, I think I might have lost it. So Jimmy, are there any questions that is there?